Hello! Hello, everybody! Welcome to the LIUniverse. I'm Dr. Charles Liu. I really would prefer it if you'd call me Chuck. It is so much fun to be here today, and I'm really glad to start off, as always, by introducing our co host, Allen Liu. Hey, Allen, how's it going?
Well, it's gone pretty good.
Oh, wonderful. You learned anything new and interesting lately?
Yeah, I've been reading about error correcting codes, which are like ways you can add extra information to a message to like make it fix itself if something's going wrong.
Whoa! An app that fixes its own code if it's messed up.
Yeah,
I
it's
love
like binary data that'll can determine if like a bit's been flipped somewhere. Yeah.
it. I wish I had that when I was typing and creating code for graduate school. Oh my gosh, how much pain and suffering that would have saved me. And it is a great pleasure to introduce our special guest today, Dr. Vivienne Baldassare. Hi, Vivienne.
Hi, it's such a pleasure to be here with you and get to talk about astronomy today.
Oh, the pleasure is all ours, Vivienne. Vivienne comes to us from Washington State University, where she is a professor of astronomy and physics. And we're having a great time today. We're going to talk about your science mostly, but other cool stuff as well. And your science specifically is, if you would tell us.
Be happy to. I search for intermediate mass black holes in dwarf galaxies. So these are black holes that are maybe 50,000 times the mass of our sun in galaxies that are a few percent the mass of our Milky Way.
Whoa! I know that that's going to be fun to talk about. Oh, can't wait to do that. It's going to be awesome. Thank you, Vivienne. Let's start today, as we so often do, with today's joyfully cool cosmic thing. Did I
Yeah.
get the order right, Alan? Did I
This
actually?
time that's the order that we usually use. Yeah.
Okay, as opposed to the joyfully cosmic cool thing or the cool
The
cosmically
cool
joyful thing.
cosmically. Yeah, there's lots of good stuff.
All
They
those
all
things
work.
are, yeah, they're all true. It's just, that's not what we're talking about. Well, today, what I'd like to talk about is something that was just recently published. It is an X-ray photo combined with a Hubble Space Telescope photo, creating composite of an X-ray binary system in a nearby starburst galaxy. I love this picture for numerous reasons because, first of all, X-ray binaries are neat and they're not very common at all. Second of all, I love starburst galaxies, and many of you know my research focuses on things that happen after starbursts. And three, it's in a dwarf galaxy nearby the Milky Way. So, Vivian, you know this system well, right? NGC 4214, and tell us about this X-ray binary and so forth.
Yeah, so this is a little starburst galaxy, and this paper presented a really interesting X ray binary system, which is when you have a compact object, which is either a stellar mass black hole or a neutron star, that is
Ooh.
being fed by a star. And in this
Mhm.
case, it's being fed by a very high mass star. And that results in a very bright system that, in this case, they've detected a whole bunch of X rays from with Chandra. And then they've
Wow.
also used Hubble to find the individual star that is feeding the black hole, which is amazing.
Wow.
Amazing. They could actually see the star itself from millions of light years away. That's just the technology continues to improve all the time, and it just so remarkable. But one thing also I would say that is that sometimes we're looking at the newest stuff, like for example JWST, which is a tremendously amazing telescope, of course, and have wonderful images, but we don't realize that the old tech is still amazing. I mean, Hubble was launched in 1990, and
You're
Chandra was
born.
launched right around the same time too, right? These
Yeah.
these telescopes are 3 decades old, and yet they're still crunching away, making amazing discoveries with them. Is so much fun, and I'm very very excited for that. So now your work, Vivian, really kind of started with these two observatories, right? The Chandra X-ray Observatory and the Hubble Space Telescope.
Yeah, I use the Chandra X-ray Observatory quite a lot to find black holes that are, in this case, more massive than the one that we might be dealing with in NGC 4214. And it's kind of funny because in my work, when we find X-rays from a dwarf galaxy, we're often trying to rule out the presence of something like this X-ray binary, and
Oh,
determine whether there's an accreting, more massive black hole there. So these are X-ray binaries are sort of a contaminant for my for my research.
foreign contaminant. I'm sorry. I still remember that line from Wally. I just have too much. Oh, that was Mo, right?
Yeah, that was Mo's internal sensor system
Right,
determining that Wally's dirt was a foreign
foreign
contaminant.
contaminant. Yeah.
Yeah,
Wow. So really, one astronomer's foreign contaminant is another astronomer's cosmic treasure, really, right? So we're
Yes.
trying to do that sort of thing. But it's fun. So you found your share of X-ray binaries that happen to be in the way of your search for intermediate mass black holes, right?
Yeah, well, the thing is that you can't always tell just from the X-ray emission alone. You'll often find an X-ray point source, so just some bright X-ray source at the center of a galaxy with some
Mm.
brightness, and you don't know whether that's from a really small black hole that's eating really fast or a bigger black hole that's eating slow. And a lot of what I do is trying to pull together other pieces of that puzzle to determine what we're actually dealing with in any given galaxy. So I bring
I
in
see.
X-ray observations and optical spectroscopy, variability information, and try to assemble the picture
Wow.
for a whole bunch of different dwarf galaxies to try to
I see.
constrain this population of intermediate
Oh,
mass black
that's
holes.
really neat. And it clearly is very technical stuff, but you were successful, right? I mean, weren't you one of like the first people in the world to have confirmed the existence of such an intermediate mass black hole?
I had a very exciting result in 2015 when I was a second year graduate student, which was very exciting.
Whoa.
um, and I
Jeez.
found a 50,000 solar mass black hole in the center of a little dwarf galaxy called RGG 118. And 50,000 sounds like a big number, but in the
Yeah.
realm of black holes that live at the centers of galaxies, it's actually quite small. So, for
Oh.
comparison, our Milky Way's black hole is 6 million times the mass of
whoa.
our sun. So, we're dealing with something much smaller here that pushes
Yeah.
into a very unexplored range in black hole mass.
Yeah,
Right.
right. Because when I hear about black holes, I hear about the supermassive ones at the centers of big galaxies like the Milky Way, and then I hear about the ones that happen from supernova, which I imagine would be like no more than like 100 something times the mass of the sun. So then, is that accurate? And like, where do these intermediate ones come from?
Exactly. So we have our stellar mass black holes, which are a few times the mass of the sun to the biggest one is I think 150 solar masses, which was found by the LIGO facility, the Laser
Oh,
Interferometer
cool.
Gravitational
Yeah.
The
Wave
gravitational
Observatory.
With
waveform. Yeah,
gravitational waves. Wow.
that's
Mhm.
cool.
Yeah, and then we have our supermassive black holes that are at the centers of all big galaxies, and those are a million times the mass of the sun and up. And then in between, we really haven't had much evidence for anything, and we're trying to figure out if that's because they're largely not there or if they're just very hard to find. And
Mm.
Mm.
whether they're there or not, and how much they weigh and where they live tells us a lot about how black holes form, what kind of formation pathways are available to us, and how they grow. So that's the bigger picture of why I'm interested in this population, besides the
Yeah.
mystery.
Now that makes total sense. Um, Let me ask. Well, you know what? Before asking the next question, let's see if there's a question from a student for Vivian. Alan, do you have a student question?
Cool. So the first one is from Lorenzo, who's asking, "Are stars only found in galaxies, and if not, where else?"
Oh, I
Hmm.
love this question. So stars are generally found in galaxies, but there's a few other places where we might find stars. So some stars live in what we call globular clusters, which are these really, really dense clusters of stars that orbit around galaxies. So any galaxy might have anywhere from a few to a few hundred globular clusters, and these
Wow.
tend to have pretty old populations of stars. So we find stars there. And then another cool population of stars that we've found are called hypervelocity stars. And these are
That
Ooh.
sounds
stars
exciting.
have been found in the halo of our galaxy, and they're
Oh.
extremely fast, as you might guess from their name, hypervelocity, and they can have speeds up to thousands of kilometers per second. And it's thought
Whoa.
that these stars get sped up by basically slingshotting around the black hole at the center of our galaxy. And they're now moving so fast that they can escape from the gravitational pull of our galaxy. So while most stars are in galaxies or clusters, occasionally you get one of these really fascinating stars, like a hypervelocity star that is just booking it on its way out. And
Wow.
Wow.
at some point, we won't be able to see it anymore. But
Fantastic.
Yeah.
Yeah, for those of you who are doing the calculation in your head right now, converting from metric to our regular English units, I'll make it easier for you. 1,000 kilometers per second is a little bit more than 2 million miles an hour. So,
Oh
so
boy.
when Vivian, you're talking about, thousands of kilometers per second, we're talking many millions of miles an hour. These guys are zipping along. Wow.
Imagine what it must be like to like view the sky from a planet around one of those stars, right? Just like
Oh, yeah.
there's like in our night sky, there's just so many stars, and yet this band of the Milky Way, you just wouldn't have that. It would be crazy, right?
Yeah.
yeah,
Just
I don't
zipping.
know if they would retain their planets.
Oh, that's a
Fair.
good point. Yeah, they must be zipping through so fast that anything that's orbiting around them might just get lost.
Yeah.
Oh, and then we wind up with rogue planets. Oh, ho, ho. That sounds like fun to think of that.
That's
Uh,
cool. Yeah,
yeah, that's
might
neat.
be able to
That's so
see the
cool.
disk of the Milky Way, like instead
Right.
of just a band. That'd be crazy.
So these orbits of these hypervelocity stars that are like slingshotting around, right? They're really highly elliptical, right? They come really close to the central supermassive black hole and then get zipped way out so that they literally escape the entire Milky Way galaxy.
Yeah, that's right. So they're very,
Hmm.
very stretched out.
Yeah. Um, you know, the that reminds me the Chandra X-ray Observatory also has that kind of stretched out orbit, right? I mean, it's highly, highly elliptical, and I don't remember why it's that way because the Hubble Space Telescope, for example, orbits almost in a perfect circle, and it's only about 400 miles or so up from the 400 kilometers or so up from the surface, or something like that, 400 miles. Anyway,
I'll check it out real quick.
you check it out. Yeah, yeah. Find out. It's several hundred miles above the surface of the Earth, and it goes pretty much in a circle. So it comes around the Earth, once every 90 minutes or so. But Chandra is not like that, right?
Yeah, that's right. So Chandra has a really highly elliptical orbit. And the reason for that is so that it spends most of its time outside of the Van Allen belts, which are these belts
Oh,
around the Earth of of a lot of charged particles, basically. And so Chandra, I think, spends about 80% of its time outside of those
Oh,
bands of charged particles. And so it can
that's why.
observe for most of its orbit when it's outside of those belts.
So during the 20% of time that's inside the belts, like they provide too much interference and make it so that the X-ray observations are harder. But when they're
Yeah,
above them, then you can see things more clearly.
yeah.
that's
Wow.
So
pretty
Chandra
cool.
is pretty
That's
amazing. One of my favorite
yeah.
telescopes to work with.
Yeah, that it is amazing, and if you think about all the things that are orbiting Earth right now, especially those things that have been orbiting for decades, I'd say Chandra is pretty cool. Hubble, of course, is also pretty cool,
Yeah.
and there are a lot of things that are, but there's a lot of stuff out there, right, Vivian? These days, a lot of things that are just orbiting the Earth.
Yeah, and things are changing very rapidly. So we currently have about 8,000 satellites orbiting
Oh
around Earth.
wow!
Most of these in relatively low Earth orbit. Um,
Oh,
and most of those at this point are actually Starlink satellites. So these are
Oh boy.
satellites being launched by SpaceX with the goal
Uh-oh.
of providing global internet coverage. And to give a little
Whoa.
context, their plan is to eventually have about 40,000 of these in orbit. So
What?
until recently, we've had a few thousand satellites in orbit. Right, we're about to
Yeah.
increase by quite a lot. And
Wow. Yeah, from a few thousand to 40,000? Dang.
right,
That
yeah, and
Crazy.
Starlink are not the only satellite constellations they're called that are planned. There's others that are planned as well that would increase that number even more. And
whoa.
astronomers have a lot of concerns about this, but
Yeah.
there's concerns beyond those to astronomy.
Yeah, no kidding. Alan, did you find out how high up the Hubble is?
Yeah. So the Hubble is 333-ish miles or 540 kilometers or so. It's in an orbit that's designed that it could have been reached by the space shuttle. So the space shuttle serviced it a few times.
Oh, I see. That's
So
true.
yeah,
The servicing was so important. That's kind of what kept Hubble this amazing, up-to-date, fire-breathing telescope after all these years, right?
yeah, right, yeah.
Well,
So
okay. So
that's about how high up it is.
and that's well below the Van Allen belts, I guess, most of the time. And
Yeah, they don't want
is
to take
that
the shuttle into them
yeah
because there might be a danger to the people's health.
right? Is well, Vivian, are all these Starlink satellites like a threat to Hubble or the International Space Station or anything? Can they actually like cause problems for like hitting them or damaging them or anything like that?
They could. So one of the things that this number of satellites requires is active communication to avoid collisions. So these satellites
Oh,
are always talking to one another to find out where the other ones are so they don't collide. But when we have outages, for example, if there's a severe solar storm and we need to put the satellites in safe mode, then the risk of
hmm.
collision um, goes up substantially. And the
Oh
more
no.
satellites that we launch, the more that risk goes up. And eventually you can end up with basically a chain reaction where you generate debris that then will collide with other things and generate more
Oh,
debris. And you could actually lose entire regions of orbit and be unable to
oh
launch
no.
anything because of the risk of collision. So
Oh,
it's a very
geez.
serious issue that I think we need to be thinking about quite seriously.
Yeah, I
Wow.
read recently that like someone had just levied like the first fine for space junk in like the history of
Really?
like regulation.
Whoa.
I don't remember the details. I'd have to find that. Maybe we can link it in the description or something like that. But that's what I
Right.
had read.
Huh.
Yeah, I heard the argument about Starlink is that like because it's sufficiently low down, like if it did start creating this thing they call it an ablation cascade or Kessler syndrome, then like it would decay within a matter of like a couple years as opposed to like staying up for a long time, which is maybe a good thing. But on the other hand, even losing like a large chunk of orbit for a couple years is not a good thing, and it would damage everything that's
No.
already up there.
And we have
Wow. That's
lots of other
amazing.
things at that orbit. So Starlink satellites are at a very similar orbital altitude to Hubble.
Oh no.
Plus, we also don't
Jeez.
know the environmental consequences of depositing that much aluminum into our atmosphere. So
That's
Oh
Starlink
also
no.
fair.
mostly aluminum.
Gee.
And if you're burning up 42,000 Starlink satellites in low Earth orbit, we don't know what the environmental consequences of that are.
Yeah, let's hope it
Right.
doesn't come to that.
Wow.
Yeah.
So that's amazing. What are the details, Alan? Do you know the details of the find? And was it like a big company, a little
Yeah,
company?
so we if you look at the information that we just got here, it's a Dish Network, so the satellite television company.
Ah,
So
yes.
they failed to remove a particular satellite that has fallen into disrepair, I guess, or just
Oh,
become obsolete or something like that. Maybe run out of maneuvering fuel. There's a few reasons
so
that
they
you
just
stop using a satellite, and they just left it there.
so they just left it there. It's kind of like if your muffler falls off your old car in the highway and you just leave it there.
Yeah, it's kind of like that. And so they were supposed to move it into an orbit that was like farther away from the orbit that anyone wanted to use. It was supposed to be 300 kilometers away from that original orbit, but they only
Hmm.
left it 120 kilometers away, and so they
Oh,
FCC gave them a fine for that.
well, I sure hope that other people get fined as well. But
I hope it's a good
uh,
precedent, because we
yeah.
gotta take care of space. There's a lot of space out there, but there's not all that much orbital space immediately above the Earth.
Mhm.
So
Yeah.
because those things are
Yeah.
zipping around so fast that each one takes up like a whole big region you just can't go near.
Wow. Oh man. Okay, let's Alan, let's go to a student question so that we can be more cheerful and
Yeah.
and find some about other cool stuff.
Yeah. So the other question we have today, this sort of goes back to something from earlier in the conversation, which is from Adrian, who is asking, how can tiny black holes swallow supergiant stars? Aren't they too big?
I love this question. This is fantastic. Yes, so black holes are um, relatively small, right, for the amount of mass that they contain. And it's a really good question to wonder how something so small can consume something really large. And it's basically thanks to tidal disruption, which is what it's called when the gravitational pull on one side of something is stronger than the gravitational pull on the other side. So
So sort of like the
basically,
tides in our ocean then. It's like
yeah.
because the ocean's being stretched at different rates. So tides, this is tides happening near a black hole.
Hmm.
Holy moly.
Yeah, so at some point, as the star is getting close to the black hole, the difference in gravity on one side and the other side will be so great that the star will start to get stripped apart and basically pulled into like a spaghetti noodle. And so it
Whoa.
will stream into a disk around the black hole and then feed it that way. And sometimes
Wow.
this can be a really great way of finding black holes that we don't know are there otherwise, because sometimes you'll
Aha.
get a really unlucky star that wanders close to the supermassive black hole at the center of a galaxy, and you'll see a huge flare as this star gets tidally pulled apart. And so
Ah.
it's a way that you can find black holes that are otherwise quiet when they just happen to get a lucky meal across their path.
How long does it take for one of those flares to happen? Is it like a matter of days, a matter of hours?
Yeah, it usually happens on a time scale of weeks to months. You'll see the
Okay.
rise in brightness over a few days or a couple of weeks. And usually, we think that the faster it rises in brightness, the smaller the black hole is. And I was
Okay.
actually part of a paper recently that found a black hole at the center of a dwarf galaxy from one of these tidal
Uh-huh.
disruption events. So
Oh
it can
wow.
be really, really great for finding, we hope in the
Yeah.
future, finding intermediate mass black holes.
Oh, so that's where the time domain astronomy comes in then. You're watching something and for a few weeks it suddenly gets brighter for no reason. You're like, aha, there's a black hole hiding in there.
Yeah, yeah. And I also look for just smaller variations, which you can get from a black hole that has a disk of material feeding it. That disk will
Hmm.
have some turbulence and that will vary over time in a particular way. So if you monitor a galaxy for months or years, in some cases, you can see these tiny little variations from the center of the galaxy that indicate there's a black hole feeding there.
Amazing. That's so cool. This these student questions are great, and it just reminds me too that students really do great science too. Yeah, you yourself made that monumental discovery back when you were a student too, right? So we should really be not like ageist or uh, like thinking, oh, feeling bad about ourselves if we're students saying, oh, I'm just a student, I can't get anything done, right? I mean, you're talking about real high quality stuff.
Oh, absolutely. And I'm always in awe of the fantastic work that my graduate students and undergraduate students do. Um, and yeah, sometimes the questions that you get when you haven't been around forever are much better.
Now, you're not allowed to say you know when you haven't been around forever because you are way younger than me, but I totally know what you're talking about. Like when I with my undergraduate students, you know, and they come in, sometimes just first year students, freshmen, you know, right out of high school a little bit, and even high school students sometimes, and they come in, I'm going, wow, how did you do that? When I was your age, I couldn't have done like 5% of what you did. But that just keeps happening all the time, and so I'm a big fan of that, and I also want to make sure everyone knows that just because you are a student or because you're earlier in your career doesn't mean that you don't have an influence, right? It doesn't mean that you can't affect things. And we were talking about the space debris issue and the constellation, you know, satellite constellation issues. One person can make a difference. I mean, I hope you, Vivienne, you know, will marshal the uh, wonderful energies of the young folks all around us to make sure that the skies and the space around Earth are preserved and protected for years and decades and centuries to come.
Yes, I hope so.
I think so too. Are there like international organizations or any kinds of uh, ways that we can participate in that if we want to be part of protecting us from this Kessler catastrophe or whatever it is?
Yeah, so the International Astronomical Union has a center for the protection of dark and quiet sky from satellite constellations. The
Mm.
American Astronomical Society has groups that are looking into this. But I think one of the most important things that we need is for people to talk about it and make folks aware and to talk to our government representatives and let them know that we're concerned about these issues and that we'd like to see more regulation around that. So I think right now raising the public consciousness is one of the most important things we can do.
Yeah, that is cool. It's almost like an extension, right, of environmental issues. You know, we care about what's under the ocean, what's at the surface of the earth, in our skies. Why not extend it further into space? It makes total sense, right?
Yeah, exactly.
Yeah, yeah. So do you love the outdoors as much as I do and Alan does?
I do, and I'm very lucky to live somewhere now that is has really great access to wild spaces. So I'm out in eastern Washington, very close to
Huh.
the border of Idaho and the Idaho Panhandle, and there's lots of mountains that are accessible. And as a trail runner and frequent hiker with my dog, that's
Oh,
been a really amazing way to get outside and see some
oh,
beautiful.
wow. So trail runner, what is that? That's like running up and down mountains just for fun and not worrying that it like is a brutal thing on the cardiovascular system.
Well, if you train
Yeah,
for it, I imagine it's a bit better.
it's not so bad. And trail runners will often hike up steep hills. So there's hiking involved in trail running.
Okay.
But
Okay.
yeah, going out to trails in the woods or in the hills or mountains, and really getting out into nature and
Wow.
and
So
yeah.
so how is it polite for me to ask like how far you run in these things? I mean, is it just a few miles at a time, especially if you're going up and down hills like crazy, or is it like
I've
marathon type
I've
thing?
gotten into running ultra marathons, so I
What?
sometimes will
Wow.
go
What?
like
Whoa.
I've done 50-mile race. That was the longest. But I've done
Oh
quite
man.
quite a few 50Ks, which are a little over 30 miles. And
Wow.
Wow.
I like to think of it as a
Oh,
long day in nature.
yeah, no kidding. Oh, how long does it take to run 50 miles at a pop?
Oh, well, it took me a long time. It took me about 15 hours, but there are folks who run it much faster.
No, that I 15 hours. I mean, I that's amazing. I would
Yeah.
be lucky if I could stay outdoors for 15 hours. I mean, I have to sit down. That's amazing, Vivian. That's awesome. Ha-
Thank
Have
you.
you been doing this kinds of running for a long time?
Um, not since childhood. I actually came to running fairly late in life.
Uh-huh.
in grad school, actually. And
Uh-huh.
I realized quickly that it was a very good stress reliever and great for
Oh, nice.
helping with anxiety. And I had a friend in grad school who was running a 5K, and I was like, you know what, maybe I can run it with her. And so we did that
Oh,
together, and I just sort of worked up to longer and longer distances. And one of the nice things about being an astronomer is that you often get to travel to amazing places. And so running
yeah.
is one of my favorite ways to explore a new city or something to do when I got to travel to Hawaii or Arizona to
Oh,
really to explore.
That's really cool.
running in Hawaii, like up on the mountaintops. Were you using
I was
telescopes?
I was at sea level, but I was using the Keck telescope. But they don't actually have you observe from the mountaintop. You are in a remote facility on the ground.
I see. But you got to run around when you weren't observing, and that's
Yes.
amazing. Now, 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 I have also been on the Big Island in the past. Alan, have you been there? Did you?
Yeah, I was briefly on the Big Island. I went to the Volcanoes National Park.
Oh, that's right. That's right. I remember that now. So that's just great. Wow. What pick an exotically memorable place that you have run that you could like describe something super cool that you're always going to remember. I mean, just it must you must have had so many cool experiences.
Well, it was my favorite memory was actually a long distance hike. I went to a conference in France and
Oh,
presented my work. And then afterwards, I went on a 7 day long distance hike around Mont Blanc by myself.
oh,
And I actually met one of my best friends. She also lives in Washington, and we've stayed in touch since then. And got to meet a lot of amazing people. And being out there by myself was really special. Um, so that's probably my kind of favorite memory from a place I've gotten to travel for work.
wow, super
Wow.
cool. All right, got to put it on my bucket list now. Okay,
Yes.
multi-day massive hike in Europe. All right, we'll make it happen. Well, are you going to go back to Europe or somewhere anytime soon to present more work? Is there anything particular right now that you're working on that's especially like cool that's going to hit the news sooner rather than later? Anything like that?
I have a couple of conferences that I'm planning to attend next year in Europe.
Hmm.
My group is also doing some really amazing work. I'm part of a survey called the Young Supernova Experiment, which is another one of these time
Oh,
domain surveys. And most of the
uh-huh.
people on the experiment are interested in finding supernovae and young exploding stars. But there's a few of us that are interested in using that data to find black holes. And I have some students working on that data and looking for these variable signatures of black holes. And we're finding some really neat stuff. So hopefully those results will be out soon.
Wow, that sounds super awesome. I wish we could talk more about that. You know, all we could talk about this all day, but we are out of time, and oh, it's so amazing. Vivian, will you come back sometime? I mean, it would be such a pleasure to keep talking about these things, this whole unexplored part of the black hole distribution in the universe. There must be so many neat things you can tell us. Please come back,
Oh,
okay?
anytime. And I think that the future is incredibly bright for intermediate mass black holes. As we get more gravitational wave observatories and more time domain observing facilities, I think there will be a lot of really amazing discoveries in the future. So I would love to come back anytime and tell you about those.
Oh, that sounds wonderful. If we want to find out more about what you do or get in contact with some of the things, is there some way we can do that? Or do you have a social media channel or a website or something we can look at?
Yes, my website is just viviennebaldassare.com. My email's on there, so you can email me or you can reach me on Twitter at Twitter / vbaldassare.
Marvelous. All right. Well, it has been so much fun. Dr. Vivienne Baldassare of Washington State University, thank you so much for being with us today. Thank you, thank you, thank you.
Thank you so much for having me. It's been so much fun.
Our co host, Allen Liu, as always, what a pleasure. Allen, thank you so much.
Yeah, you're welcome. Glad to be here.
And for all of you in the audience, thank you so much for being with us today. If you like what you see and hear, please support us on Patreon. And as always, thank you for being a part of the LIUniverse.